Okay, so today we're going to talk about a little bit kind of a different strategy with respect to some of these synthesis problems. Okay, so the first part of this chapter kind of reviews what we know already, right? So we talked about how to change the position of a functional group, how to change the position of a pi bond. We also know how to introduce functional groups via our radical reactions. We know how to extend a carbon chain via the alkylation reaction that we learned. And so now we're trying to, in this chapter, kind of bring all of that stuff together so that we can go about solving these synthesis problems. And again, with respect to these synthesis problems, you're always going to be given whatever your starting material is, right? So you're always going to be given whatever your reagent initially is, and you're also going to be given the product by which we're wanting you to actually synthesize, right? And the question is, how do we get from A, or our starting material, to B, right? What are the reactions required? What are the reagents of those reactions, and what order do we need to do them, okay? And so the first part of this chapter dealt with kind of more simple problems, right, where we only had maybe 1 to 2 to 3 different steps in getting from our starting material to our product. But as we get deeper into some of our reactions and as we expand our toolkit with respect to these reactions, these problems are going to get a lot more difficult, and they're actually going to require a lot more steps involved, okay? So as they do get more difficult, we try to kind of rearrange how we look at solving them, or we try to kind of shift our minds into trying to solve these problems in a different manner, okay? And so that's what the end of this chapter deals with, is something called retrosynthesis, okay? This is this new framework by which we're going to try to have you guys solve these synthesis problems, okay? Now, again, thus far, what we've been doing is kind of taking all of these synthesis problems in the forward direction, right? You usually look at your starting material and you look at your product and you say, how can I get from A to B, right? How do I move in the forward direction in getting from A to B, okay? So you imagine, well, what can I make from my starting material that kind of gets me closer to my product? Now, with retrosynthesis, again, we're trying to reframe how we look at this. We're actually going to move in a different direction, right? Instead of moving in a forward and going from our starting material to our product, we're actually going to move in what we call the reverse direction, right? So the first question that we are going to usually ask in a retrosynthesis problem, so this is our reverse direction, is what can make our product, right? How could we potentially make our product, or what type of material or compound will we need to make the product that we're trying to answer, okay, or try to make? And so that is the idea of retrosynthesis. Instead of taking this in the forward direction, we're actually going to try to synthesize this by taking reverse steps each time, right? What can make my product? Once I'm at this, once I know what this looks like, what can make this, right? And then once I'm here, what can make this potentially, right? It's moving this in the reverse as opposed to moving it in the forward direction. Okay, so again, with retrosynthesis, we're going to continue to ask those same questions that we talked about at the beginning of the chapter, right? Number 1, what happens to the carbon skeleton, right? Do we extend the carbon chain? Does it decrease in carbons? And then number 2, what happened to the functional group? Did it change location? Did it change its identity? Okay, we're keeping those 2 in mind, but again, instead of going this way and trying to synthesize our product, we're actually going to go in reverse this way and say, what compound could have made our product? Okay, so we're going to answer that at this point in time, right? Our product long term is an alkyne, and the question is, well, what can synthesize or what can make an alkyne? We've only talked about one very specific reaction where we can make an alkyne from something else, and that came in that Alkyne chapter, chapter 9, right? The only way that we can make an alkyne is via a dihalide undergoing successive elimination reactions, right? So we can just leave this right now as a dihalide because there's a couple different ways that we can have a dihalide. So we can just say this is a dihalide. And again, what I mean by dihalide is, again, 2 different halogens, or like 2 different bromines, 2 different chlorines That dihalide then needs to be in the presence of a very strong base, and it needs to be excess, and that strong base is sodium amide. And then again, at the end of this, if we just leave it in the presence of excess sodium amide, we would get the alkynide ion at the end. So this also needs to be followed by water, right? This is a reaction that we have talked about, that we have discussed. Taking a dihalide, having it be in the presence of excess sodium amide, which is a very strong base, followed by a workup with water, producing an alkyne, okay? Again, if you guys don't remember that, you need to. You need to go back and you need to look at it, okay? All right, now the question is, well, what does this dihalide have to look like, right? And so we had talked about, when we talked about this reaction, that we have a couple of different options for this dihalide. So number one, the dihalide could have been what we call geminal, right? So to make this alkyne at the end, we can have a geminal dihalide. Again, in a geminal dihalide, the halogens are on the same carbon, right? So it could have been on this carbon. Another thing that could have synthesized this alkyne at the end was another different geminal dihalide, right? So now both of the halogens are on this carbon. And another thing that we could have used to synthesize this alkyne was instead a vicinal dihalide, right? So all of these guys, vicinal, all of these guys could potentially generate the alkyne that we're trying to make at the end of this, right? So again, we're taking a step back. We're saying what can make an alkyne? All of these three things could potentially make an alkyne if they are reacted with excess sodium amide and then followed that with water, okay? Now the question is, well, which one, right? How do we know which one we're actually going to need to make? Now, for the geminal dihalides, we're going to take that next step back, right? We're going to say, well, what is going to make a geminal dihalide, right? Because again, we're taking these steps in reverse. We're trying to, this retrosynthesis approach. We have only seen one reaction that can produce a geminal dihalide at this point in time. And specifically, that was a reaction that was an alkyne addition reaction, right? If we wanted the Markovnikov geminal dihalide, then essentially what we would do to make that would take an alkyne, have that undergo a hydrohalogenation reaction that would have given us the geminal dihalide in the Markovnikov fashion. We could have also generated the geminal dihalide via a different hydrohalogenation reaction, right? So again, if we had excess HBr, but now this guy instead was in the presence of peroxides, this would have given us the anti-Markovnikov. So this is anti-Mark geminal dihalide. This guy would have given us the Markovnikov geminal dihalide, right? But again, the purpose of this is making this alkyne, right? So there's really no point in taking an alkyne, making it a dihalide to make an alkyne. We've already gotten to the end if we've already made this alkyne, okay? So because of that, we know that we can't use either of these two geminal dihalides, right? This is not going to be the thing that makes our product. This guy's not going to be the thing that makes our product, okay? So that leaves us with the vicinal dihalide, right? The vicinal dihalide will give us our overall product. Now the question is, well, what would make this, right? How do we know how to make a vicinal dihalide? Okay, so now the answer to that question, what type of compound can make a vicinal dihalide? The only thing that we have really seen thus far that can do this in our repertoire of reactions is an alkene, right? We do know how to take an alkene and turn it into a vicinal dihalide, right? Ideally, you guys are going, oh yeah, I know how to do that. That is that halogenation reaction, right, where we would have bromine in the presence of some non-nucleophilic solvent. This was one of our addition reactions, right? It goes through the bromonium ion intermediate. The bromines add in an anti-fashion. We get our vicinal dihalide, okay? So that's the next step, right? We need an alkene to get to that dihalide to get to the alkyne, okay? Okay, so whenever we're doing retrosynthesis, we kind of use something that's a little bit special, right? So thus far, we've always been using our normal forward type arrows. But when we're doing this retrosynthesis analysis, we're going to use a special arrow called a retrosynthesis arrow, right? And so as we're doing this guy right here, and I'm not going to draw it because it's already drawn, is what we would consider a retrosynthesis arrow. And it's going to help us understand how we can make our desired product starting from whatever material is required to make it, right? So in this retrosynthesis type problem, I would take my Alkyne, I would have my retrosynthesis arrow, and that's supposed to be signifying this thing can be made from this thing, right? So then in our second retrosynthesis step, that vicinal dihalide, if we use our retrosynthesis arrow, can be made from an alkene, okay? So now the question is, if we remember at the very beginning what we started with, right? So our starting material was an alcohol, right? Again, long term, we wanted to go to the alkyne. And at this point in time, we know how to get from the alkyne to that vicinal dihalide, right? So we were here, and bromine with this guy. Let me actually draw that better. So we knew how to get from the vicinal dihalide to the alkene. Again, this was excess sodium amide, followed by water. We knew how to get we knew how to produce that vicinal dihalide. The only reaction that we have available to us for that is taking an alkene and undergoing that halogenation reaction. So this was bromine in the presence of carbon tetrachloride or another non-nucleophilic solvent. And so now the question is, okay, if we take another retrosynthesis step, we go in reverse again, what can make an alkene, right? But also at this point in time, we should be able to kind of pull in from that original stuff that we talked about that we do know how to get from here to here, right? We have a alcohol. We do know how to turn an alcohol into an alkene, right? So now at this point, instead of going necessarily in reverse, we now kind of are at that point where we can go in the forward direction. How do I get from this guy, our alcohol, to our alkene, okay? So there's a couple of things to note with respect to our alcohol and taking our alcohol to this alkene. First off, important thing to note, we do know how to take an alcohol and make an alkene. We know that is an elimination reaction, right? So taking a leaving group or a functional group, trying to turn it into an alkene, that's going to require an elimination reaction. But the problem with this at this point in time is that alcohols are bad leaving groups, right? So an alcohol is a bad leaving group, a bad LG. And so, well, we had a couple different means by which we could deal with that, right? One of them was what was called acid catalyzed elimination, right? So this was H3O plus, right? That H3O plus would protonate the alcohol, making it a much better leaving group because it would leave as water. But the problem with that was that acid catalyzed elimination was an E1 mechanism, right? And E1 mechanisms were only good for tertiary alcohols, right? Unfortunately, this is a primary alcohol, right? The alcohol is on a carbon that's only attached to one other carbon. And so because of that, we can't use this acid catalyzed elimination to actually get from our alcohol to our alkene. Instead, we have another means by which we could turn that bad leaving group, that alcohol, into a good leaving group. And so to do that, we are going to turn that into a tosylate, right? So here we would have our tosylate as our leaving group. To get from an alcohol to a tosylate, we know that we need tosyl chloride in the presence of pyridine. And now this is a good leaving group. To get to our alkene, all we need to do is have a strong base, right? Again, we need to consider regiochemistry here, but there is no regiochemical preference here. There is no Hoffman versus Zaitsev because, again, we have a primary alcohol. So you can use just some nice strong base. You could use something like Naomi here to undergo that E2 elimination, or you could use something like terbutoxide. Again, you have to consider the regiochemical needs of whatever reaction you're dealing with, but that doesn't necessarily matter right now, okay? All right, so then that's it, all right? This guy has 1, 2, 3, 4 different steps, and again, the purpose of looking at this in reverse is essentially kind of getting us to this point where we were at, right? Where we could see how to take our starting material and how to get to whatever step we were at in the overall synthesis, okay? But we kind of needed to do these guys first before we could get there. Okay, so then once you're there, right, you just need to make sure and to kind of answer the final portion of your problem is to collect all of those various steps, right? So to take our alcohol and turn it into our tosylate, we needed tosyl chloride and pyridine. To take our tosylate group and undergo that E2 elimination reaction, we needed a base, right? This could be terbutoxide, like we said, or you could use Naomi. Again, once we have the alkene, to take it to that dihalide, that vicinal dihalide, that was our addition reaction, our halogenation. That was bromine in the presence of carbon tetrachloride. And then once we were at our vicinal dihalide, to get it to the alkyne, we needed to use that strong base, sodium amide. It needed to be in excess, and that needed to be followed with a step with water that protonated that alkynide ion and gave us the terminal alkyne at the end. Okay, so again, those are the steps. For the correct, complete answer of this, you would have collected all of these guys over and above the arrow, and that is how you would get from this primary alcohol to this terminal alkyne. Okay, so with retrosynthesis, it's really easy for me to be like, oh yeah, you do this, you do this, you do this. But probably the best way to go about doing a lot of these is just to get practice. Okay, so I have 2 problems here. They're a little bit more difficult than the practice one that I just did. Again, the first step in all of these is going to be some sort of question of what happens, number 1, to the carbon chain, right? So do we extend our carbon chain? And then number 2, what happens to the functional group? So functional, let me write that correctly. Functional group, number 1, does it change identity, right? And number 2, does it change location, okay? So that should be number 1, that should be first. Now, as you try to answer these guys, again, I'm going to insist that you try to use this retrosynthetic analysis type solution, right? So I'm going to take this guy and pull it down here. And so the first thing that I would, ask you to do is to say, okay, this is my product overall. How can I make this product, or what compound could I make this product from, right? Again, we are limited at this point in the type of reactions we have. So, for example, to make an aldehyde, there's only one reaction that we have that can make an aldehyde, right? So consider that, right? What is that one reaction that we've talked about that can make an aldehyde? What does that require, right? What starting materials that require, and how do I get to that aldehyde? What are the reagents I need? Once you're here, then I would do it again, right? How do I make whatever this guy is, right? What could that have come from? I would continue to do that until it does become apparent how to get from here to whatever step you're on, okay? All right, so again, go ahead, take some time, do both of these, and I'm going to go over the answers after the break, or pause the video, do whatever you want, but I'm going to go through the answers following your attempts. Okay, so I'm going to start with A here, and I'm going to go ahead and erase all this stuff below. Okay, so again, with respect to retrosynthesis, right, we're going to try to take this in reverse, right? And so ideally it's going to be a little bit easier in seeing the answer when we do. Now, again, we're going to start with the same questions that we were asking before. First off, what happens to the carbon chain? All right, so for A, we have 1, 2, 3, 4 carbons. So we have a 4-carbon compound. As we move to the product here, we've got 1, 2, 3, 4, 5, 6 carbons, right? So yes, the first question, what happens to the carbon chain? The answer to that is we extend the chain by 2 carbons. Okay, so we do change the carbon chain. Number 2, the question is what happens to the functional group? So we take an alkene in our starting material and we convert it into somehow an aldehyde. Right, and so the alkene is in between carbons 3 and 4, and the aldehyde is on carbon 6. So both the identity as well as the location change in this overall reaction. Okay, so we take an alkene and we make an aldehyde. And again, we do also change the location. Okay, so now the first question in my mind that I ask is, all right, our product is an aldehyde, right? What reactions or what overall reaction from what type of compound could generate an aldehyde given the reactions that we know right now, right? Again, we are very limited on the type of reactions that are going to generate things like an aldehyde. So specifically, there is only one reaction that we know that can make an aldehyde, okay? And so if we go back to the Alkyne chapter, right? So this is alkynes. The question again is, what can generate this? This can be generated from a hydroboration oxidation of a terminal alkyne. So we have 1, 2, 3, 4, 5, 6. So actually, if we go back here, we have 1, 2, 3, 4, 5, and then 6. So again, make sure you count your carbons. 1, 2, 3, 4, 5, 6. If we take an alkyne, and again, we hydrate it in an anti-Markovnikov fashion, the first thing that is produced is an enol, but again, that tautomerizes into an aldehyde. Okay, so what we're looking at here is taking an alkyne and undergoing this anti-Markovnikov hydration reaction. Again, this was, another word for this was that hydroboration oxidation of a terminal alkyne. Okay, all right, so hydroboration oxidation. If you guys think back to the reactions, the reagents that are going to generate that, we know the hydroboration oxidation uses borane, so BH3 in THF, and that's at a first step. And then in the second step, it's oxidized, so we use H2O2 NaOH. Now, the only problem with the BH3, the borane, is that because the alkyne has 2 pi bonds, it can add, both of those can add to the borane. So because of that, the only little change we had to make here for our hydroboration of an alkyne as compared to an alkene was that we couldn't use BH3. Instead, we used a dialkylated borane. So this could either be that 9-BBN, followed by, again, the H2O2 sodium hydroxide, or there was the diisoamyl borane. But again, I said you should use 9-BBN because it's easy to remember that, okay? So that's number 1, right? We do know how to make an aldehyde, and that's going to come from a 6-carbon alkyne, pardon me. Okay, so now the question is, we've got this reaction that can produce our aldehyde. What's next, right? How do we generate an alkyne? Okay, so again, we're going to have to keep in mind the fact that we're going to generate an alkyne, but we're also going to have to extend the carbon chain by 2 carbons. Okay, so that should give you some indication of maybe what the next reaction is going to be, right? Again, the only way we know how to extend the carbon chain is via that alkylation reaction, right? And specifically, if we take something like acetylene and deprotonate it and add it to a primary alkyl halide, that's going to extend the carbon chain by 2 carbons. It's also going to introduce the alkyne functional group, right? So again, what I mean by that is if, let's say we had a 4-carbon alkyl halide, so something like 1, 2, 3, 4, right? So something like this. If we took this and we reacted it with deprotonated acetylene, right, that acetylide ion. So to write that, we could just say Na plus and then CH minus, right? That's that acetylide ion. This guy acts as a nucleophile. It attacks that primary alkyl halide at the alpha carbon here, right? And it undergoes this SN2 reaction. The product of that reaction would have 1, 2, 3, 4, 5, 6 carbons, and it would have that alkyne at the end, right? That stays there, right? So again, if we labeled these guys 1, 2, 3, 4, then this would be 5, 6. We have 1, 2, 3, 4, and then we have 5, 6, okay? So again, it's that coupling the fact that you know you're dealing with an alkyne and you know you have to extend the carbon chain. That's going to kind of lead to the fact that, well, there has to be an alkylation reaction somewhere, and alkylation reactions always have those carbon-carbon triple bonds. Okay, so now the question is, well, okay, we're at 4 carbons here. We're at 4 carbons here. Is there any way that I could take my starting material, my alkene, and get us to where we are right now, right, which is this alkyl halide? And the answer to that ideally would be yeah, right? This is just an addition reaction. It's an addition of HBr, right? Where the H goes to carbon 3, the bromine goes to carbon 4. But no, this is not just that normal hydrohalogenation reaction. Normal hydrohalogenation reactions would give us the Markovnikov product, which would have put the carbon, or would have put the halogen here. Instead, we're getting the anti-Markovnikov product here. So this is anti-Mark. And the only way we know how to do that is with our HBr, but this needs to be in the presence of peroxides. That is that anti-Markovnikov hydrohalogenation reaction. Okay, so then that's it, right? We do know how to take a 4-carbon alkene and make this primary alkyl halide. That's via that hydrohalogenation, anti-Markovnikov fashion, so it's in the presence of peroxides. And that's essentially the entire synthesis, right? So now what I would do is I'd go ahead and collect everything in the individual steps. So the first thing we're going to do is take that 4-carbon alkene. We're going to have HBr in the presence of peroxides. That's step number 1. Step number 2, we're going to react that, the product of that, with our Na, our acetylide ion. So you can draw that like this. And this guy was our minus. That's going to give us our 6-carbon alkyne. Once we're at the 6-carbon alkyne, then we're going to undergo that hydroboration oxidation, right? So the first step of that is that 9-BBN. And then the last step is the oxidation part, the H2O2. And sodium hydroxide. Okay, so that is number 1, or that is A. So again, if you haven't done B, I would try to do B before you move on. B gets a little bit harder, a little bit more complex comparatively to A. I'm going to go ahead and copy it, and I'm going to move it. Oh, I don't want to do that. I'm going to move it over here. Okay, oops. Okay, so let's go ahead and talk about B. So B is going to get a little long, just to give you a warning. So again, the first question that I'm going to answer right now, or first question I'm going to ask is, what happens to the carbon chain? Because again, that's going to help inform a couple of the different reactions I'm going to necessarily need. So right here, we're going to ignore the cyclohexane part, right? The ring doesn't change, it's the same. But I'm going to count this carbon as 1, 2, 3. So we have 3 carbons in our starting material. And I'm going to go over here, count 1, 2, 3, 4. We move to 4 carbons in our product. So we do extend the carbon chain by 1 carbon. And then number 2, we're going to ask about the functional group. So the functional group is an alkene. In our starting material, it is also an alkene in our product, except it does move position, right? So it's in between carbons 1 and 2 in our starting material. It's in between carbons 2 and 3 in our product. So no to identity. That doesn't change, but yes to location. Okay, so now we're going to keep that in mind as we're going through this retrosynthesis. All right, so the first question I ask is, number one, how can I generate this alkene, or what could this have come from, right? What are the only ways that we can generate an alkene in maybe just one step, right? So if I think back to all of the reactions, I also consider the fact that I'm probably going to have to add a carbon at some point, and that's probably going to need to go through a carbon-carbon triple bond. One way that I could generate an alkene is via a reduction of an alkyne, right? So we had a couple different reactions that could take an alkyne, and generate an alkene. And the reaction that we were going to use depended on the type of alkene that we wanted to produce. Specifically, this is a trans alkene. So we could take an alkyne, and generate a trans alkene via that dissolving metal reduction. So this was sodium in the presence of liquid ammonia. All right, so that is probably the first step, is taking an alkyne and turning it into an alkene. Next, the question is, okay, well, we have an alkyne, we have a carbon-carbon triple bond. We know we're going to need to extend the carbon by one carbon, the carbon chain by one carbon. So perhaps what came before this, and maybe I should go down so I give myself room, was the 3-carbon alkyne, right? So we could take, let's say, let me erase this because this is ugly. We could take a terminal alkyne, right, that has 3 carbons. We could react that first with a strong base, sodium amide. And then we could, that would deprotonate our alkyne to make it the alkynide ion. Then we could use that as a nucleophile to whatever length of carbon we needed to add it to, right? We only need 1 carbon right now. So once this was deprotonated, it was not, I hate when it does that. Once this guy was deprotonated, after the addition of that sodium amide, all we really needed at that point was something like a methyl iodide or a methyl bromide, right? Again, this guy's going to act on the alpha carbon. The carbon's attached to the halogen. This guy's going to leave, and that would extend our carbon chain by 1 carbon, okay? Again, we're not necessarily concerned with this. I'm not concerned about the mechanism. I just want to know what the reagents are that are going to get me from here to here, right? And so this is my whatever reagent or my starting material, whatever I'm at right now. If I combine that with sodium amide in the presence of a methyl iodide, that would take me from this guy and get me to that guy, this guy. Okay, so now the question is, we've removed one of those carbons, or we're at the point where we only have 3 carbons to deal with, so we're done with that whole carbon chain thing. Now the question is, how do we get from a alkene that's in between carbons 1 and 2 to an alkyne that's in between carbons 2 and 3, right? And so this is going to kind of be that whole, like, moving the position of a double bond, added into the fact of not only moving the position, but also the fact that you're having to make an alkyne from it, right? So again, if we go back to the original example that I gave you guys, the only way we know how to make a carbon-carbon triple bond is via that successive elimination. So I'm going to go down here. I'm going to redraw this guy. We do know how to make a carbon-carbon triple bond, but to do that, we need a dihalide, right? Again, we need an excess of sodium amide, and then secondly followed by water. Now the question is, well, how do we generate that dihalide? And again, the answer to that is, well, we can utilize our bromination reaction, our not radical, but our halogenation reaction, right, where we have a double bond between carbon 2 and carbon 3 in the presence of bromine in a non-nucleophilic solvent, we get the dihalide, right? Now we're at the point of how do we move the position of a double bond, right? So we had a double bond in between carbons, or a pi bond in between carbon 1 and 2. Now it's in between carbon 2 and 3, right? So this is going to be, again, an addition followed by a successive elimination. If we want to add a halogen at this position, which is what we want to do, again, this is going to be an addition reaction. This would be HBr. But again, if we want the halogen to go to carbon 2, which is what we do because we want to eventually eliminate it between carbon 2 and carbon 3, this is not the Markovnikov product. This is the anti-Markovnikov product. So this is HBr in the presence of peroxide. Now that's going to be followed with an elimination to get us to our alkene between carbon 2 and carbon 3. And again, this elimination, it's specific, it's regiospecific. We specifically need the Hoffman product, not the Zaitsev product. And so because of that, we're going to have to use our bulky sterically hindered base. So this is tert butoxide, and that would give us our product. Right, so again, this is what I mean by them getting kind of extreme, and why retrosynthesis is very, very, very helpful, right? Again, especially with respect to where we're at right now in the semester, we do not have a lot of reactions that can do a bunch of stuff, right? So we are very limited in some of the various reactions that we can perform. For example, making that transalkene going from here to here, there's only really one reaction that we have. It's that dissolving metal reduction of an alkyne. Extending a carbon chain, we only at this point have one way to do that. So we know we're going to be moving through this alkyne intermediate at some point in time. Making an alkyne, there's only one reaction by which we can do that, right? And then moving the position of a pi bond, it's always going to be an addition reaction followed by an elimination reaction. Okay, so overall for this reaction, there's a lot to keep in track of, and I'm going to go ahead and try to write it as neatly as possible up here. So the first step, we had an anti-Markovnikov addition of a hydrohalogenation reaction. So this is HBr in the presence of peroxide. In step 2, we had an elimination that gave us the Hoffman product. So this was a bulky base, tert butoxide. This was followed by a halogenation reaction. All right, so we got the dihalide. So this was bromine in the presence of a non-nucleophilic solvent, like carbon tetrachloride. Then we underwent the successive elimination. So 4 was excess sodium amide to produce that alkyne. In 5, again with the presence of excess sodium amide, we generate the deprotonated alkyne. We need to make sure and protonate it before we can move on. So we add water. So then for 6, we then deprotonated that alkyne again. And then added it to, of course I just ran out of room. We deprotonated that and then added it to the primary methyl iodide, the primary halogen, or the methyl halogen. That gave us our internal alkyne with the 4 carbons off of the cyclohexane ring. Again, we had the alkyne, we need to turn it into the transalkene, so that gave us step 8, which is that dissolving metal reduction. Sodium metal in the presence of liquid ammonia. And I'll go ahead and rewrite this guy. And ROOR. Alright, so that's it. Alright, overall, we had 1, 2, 3, 4, 5, 6 separate reactions to get from our starting material, an alkene with 3 carbons, to our product, an alkene with 4 carbons. Okay, so again, best way to go about doing these is to just get practice. I do want to kind of mention a couple things before I'm done with this, and then I will upload it, and I will open up the homework for chapter 10? Chapter 11. Why did I name this chapter 9? Okay, anyways. Okay, so just a couple things to keep in mind as you move through the problems, and then as we move into the next few chapters, which I think we're only going to deal with alcohols in the next chapter, and then we'll move into pericyclic reactions for the last thing we talk about. But again, with respect to synthesis, it's kind of helpful to keep a couple of things in like a little list just to keep handy on you. So for example, when we ask these questions, right, what's happened to the carbon chain or what's happened to the functional group, you could kind of go ahead and keep like a toolkit of the reactions that can change the carbon chain or the reactions that can transform a functional group handy, right? So for the carbon chain right now, or, you know, messing with the carbon skeleton, we really only have one that we've talked about kind of extensively, and that's just that alkylation reaction. In the next chapter, we'll add on to that, so we'll be able to extend the carbon chain or create carbon-carbon bonds in another way. But that kind of list of ways that we can do this is very short at this point in time. Now, a separate list of how you can transform functional groups, that's going to be a little bit longer, right? And so, again, trying to keep these 2 separate goals in mind and how you can go about doing that is going to be helpful. Second, it could also be helpful to build your own synthesis problems. So, for example, you could start, let's say, with acetylene, and you could go through and say, okay, what do I want to do to acetylene? All right, so for example, if we started with something like acetylene, you know, what type of reactions can you deal with acetylene? Well, first off, you could add it to another carbon chain. So, for example, we could go ahead and deprotonate it with our sodium amide. And then let's say we can extend it on one side with like an ethyl iodide, right? So that would take our acetylene and it would extend it by 2 carbons. Let's say that we did that again. Let's say we did it to the other side this time. So let's say something like sodium amide again, and now we add it to, let's say, methyl iodide, right? So the reaction there would give us a 1, 2, 3, 4, 5 carbon. And now let's say we took that and let's say we reduced it using that hydrogenation reaction. Let's say that we wanted to boost the trans alkene here. So again, we could say, okay, sodium metal in the presence of liquid ammonia. That's going to give us the trans alkene from that, where we have, make sure I keep track of this guy, 1, 2, 3, 4, 5, right? And so there is essentially a practice synthesis, right? You just created a means by which you could take this guy and go through and make this guy, right? And so you could do that for a bunch of different things. Just make up reactions just to kind of get a feeling for how some of these patterns are going to start forming. Like, how do we take and add 2 carbons? How do we take and add 1 carbon, etc. And then finally, a couple of things to note. One last thing is a lot of times when we deal with synthesis, there are going to be more than one way that you can go about solving a problem, right? That last problem had 6 steps in it, which was pretty long. You're going to find problems that are going to be long like that. But ideally, what we're looking for is the most efficient pathway to get from starting material to product, right? So let's say that there was some sort of starting material and you guys figured out a pathway to get to the product and it took like 10 steps, right? That is valid, right? That is a valid synthesis, but that's probably maybe not necessarily the correct answer. If you could also come up with a way to get there in 3 steps, then the 3-step pathway is the best pathway to go for, right? You're going to find that you're going to kind of get lost in the weeds sometimes with some of these and keep, moving through these various functional groups. Ideally, we want our our best synthesis to be the most efficient synthesis, right? And so that's going to require the least number of steps. So keep that in mind as you move through these. Okay, so that is it for this chapter. Again, practice. This is why I've kind of, indicated that you guys need to know those reactions from, all the way from substitution to elimination to addition, because this is when, you need to have a good foundation on how to go from one thing to another. Okay, so good luck. Email me if you have any questions.